Again, welcome to Mathematics 200 MAT 200. This is Business Calculus class at New Jersey City University. In these lectures, we're going to discuss about applications of Maxima and Minima, normally used in business applications. In our previous lectures, we discussed how to find the maxima or minima values of a function. That's the absolute maxima and also absolute minima. Normally, when we have the original function, we will find the first derivative of the function. After we find the first derivative of the function, we are going to equate it to 0, and that will help us to find the critical value. When we get the critical value, we substitute the critical value in the original function, and the answer we get will be the absolute minimum or maximum. Now, if the function open upward, it's called minima. If it open downward, it's called again maxima. So in these lectures, we're going to apply the concept of finding maxima and minima to solve problems from management, life, social sciences. So this is our first example. The example here says, suppose that a new company begins production in 2015 with 8 employees, and the growth of the company over the next 10 years is predicted by the following function. So we have n at t. Again, t is the time period, and the time domain is from 0 years to 10 years. And the question also said within the next 10 years predicted. So our time is between 0 to 10 years. And the function is 8 parentheses 1 plus 160t over t squared plus 16, where the n is the number of employees t years after 2010. We know a company growth with the number of employees also will increase. So this is our equation here. It will give us the prediction of the number of employees we may have between the years 0 to 10 years. So now the question said, determine in what year the number of employees will be maximized and the maximum number of employees. So here we want to find the absolute maxima. We know as time goes on with between 0 to 10 years, employee will be, size will be increased. But what particular here between 0 to 10 that the employees will be maximized? Or we may have the maximum number of employees within that 10 years period. And we can't say in 10 years or 9 years, because maybe some, by the 5th year, we may have a lot of employees. Then maybe based on the function given, they may start to reduce. So by the 7th, 8th year will be lesser than in the 5th, 6th year. So we don't know. But based the function here will tell us everything. So our goal now is to find the absolute maximum. So the first thing we have to do is to find the first derivative of the function. We know the derivative of 1 is 0. Here we have a division. We have to apply the quotient rule because we have a variable t at the top and variable t at the down. So we have to use the quotient rule. So when we use the quotient rule, this is what we get. We square the denominator, then we multiply the numerator, the derivative of the numerator with the denominator. So we have the denominator here multiplied by the derivative of the numerator, minus derivative of the denominator multiplied by the numerator. So the numerator is 160t. The derivative of it gives us 160 times t squared plus 16 minus the derivative of t squared plus 16 will give me 2t times the numerator. Everything squared. So here we are going to simplify this expression, open the parentheses, combine the like terms, and this is what we get. From here also we can still keep going. We have t squared, we combine, and we get this. Then from the function here, we can see that again, the 8 may not mean much. we are going to equate this function to 0. So if I equate this function to 0, 8 will be 0 divided by 8 will give me 0. And I'll multiply t squared, 16 all square goes to the left, multiply by 0, everything will be 0. So at the end, we are going to get 0 equal to 2560 minus 160 t squared. And this will give us, we factorize the expression, we get 160, 4 plus t, 4 minus t. So 160 is common. 160 can go into 2560, that's 16 times. So we get 16 minus t squared, and that gives us difference of t squared. So from here, we know 160 with 0 will turn to 0. So we are going to get 4 plus t equal to 0 and 4 minus t equal to 0. Our answer will be positive 4 and negative 4. But again, here we are dealing with time. So we are going to use the positive 4, not negative 4. The t is time. So we are using positive 4. Now we are going to plug the positive 4 in our original function. And this is what, first we're trying to find the relative maximum. That means we didn't plot, again, most of the time we skip this section in our previous lecture because I can plot the graph, the original graph, the function graph, and I will know whether our answer will be either maximum or minimum. If the highest point open up and downward, or the lowest point, the graph open upward. But again, we can test, we know how to find the relative maximum and minimum. We are going to test the interval of the values. So here we can use, if t is 4, we can use any value less than 4, any value greater than 4, and the 4 in the middle. But when we use the values, 4, we plug it in the original function. This is what we get. The value is greater than 0. And we plug negative 4 into the function. Again, we get less than 0. So here we will see that we have increasing to decreasing. So increasing to decreasing will give us relative maximum. Decreasing to increasing will give us minimum. So now we plug our 4 into our original function. Again, the original function is given to be here. So I'll plug 4 here, 4 square, then we simplify everything here. So that's what we saw there. And when we are finding the relative minimum or maximum, you will see that we use the derivative of n sub. But when we are finding the maximum, which will be the absolute maximum or minimum, we use the original function, n. So we plug the value, this is what we get, 168. So this means at t equal to 0, the number of employees is n equal to 0 will be only 8. So when we start with t equal to 0, we are going to get 8. But as time goes on, when we reach the 4th year, we plug 4 in our original function, we get 168. And that's the maximum employee we can get, so in the 4th year. So here we say after t equal to 4, which is 2040, n at t decreases to n at 10, that will give me 118. So n at 4 years, give us 160 will be the maximum. So we have the value 4, we can try any value 6, 7, 8. We will see that the answer will be less than 168. Any value we try between 0 to 10 will be less than 168. 4 will give us the maximum. And again, the steps we did here, we have the function. So the first thing we do is to find the derivative of the function. Then when you get the derivative of the function, you equate it to 0 to find the critical value. it's like we are finding the relative minimum or maximum. So when we get the critical value, we're going to set an interval. So here we have -4 and 4. So we can set our interval, the interval, and also remember the domain is from 0 to 10. So I can't use positive or negative infinity. So in this case, I have to take -4 out and then use from 0 to 10. So I'll put 4 in the middle, and I'll test any value between 0 to 4 and also between 4 to 10, a little bit greater than 4, a little bit less than 4, or even 0. So there we can see whether we have decreasing to increasing or increasing to decreasing. If we get the function to the left, the value a little bit less than 4, give me a positive value, that means it's increasing. To the right, more than 4, give me negative answer, then it's decreasing. So we get a maximum, relative maximum. The opposite will be relative minimum. From decrease to increase will give us relative minimum. So after we get that concept, then we know here when we did it, we know that we have relative maximum. So now I'm going to plug the critical value into the original function. This will give us the absolute maximum, and that will be the number of employees that we can get in 4 years. Remember, the 4 years is the critical value. So when we plug it again, this is what we have, and we can see the maximum employees. Again, is the 4th year. It's the 4th year. So let's try another example. Here we say the application of maximum and minimum. Sometimes we must develop the function we need from the statement of the problem, which will be our next example. In this case, it's important to understand what is to be maximized and also minimized, and also to express that quantity as a function of one variable. So our previous example, we saw that example 1, the function was given to us, so straightforward. Now in this case, we have a question saying that a farmer needs to enclose a rectangular pasture containing 1,600,000 square feet. So it's again 1,600,000 square feet. Suppose that along the road adjoining his property, he wants to use a more expensive fence, and that he needs no fence on one side, perpendicular to the road, because a river bounds his property on that side. So doesn't need a fence because of the river. Now the question said, if the fence costs $15 per foot along the road and $10 per foot along the 2 remaining sides, that will be fence, what dimension of rectangular field will minimize its cost? So here we have to get into finding absolute minima. So the same step, but again, in this case, we don't have the function. We have to understand the concept and come up with the function. So this is how the fence look. We remember the question said that one side have a river, so we don't need a fence there. So this is the river. On the main road is $15 per square. Then different price for the other side, $10 and $10. So we represent S as the length of the pasture along the road and parallel to the road, and Y represent the width. So this is Y, which also is $10 per. Again, we can see the fence costs $15 per foot along the road and $10 per foot along the 2 remaining sides. That must be fence. What dimension of rectangular field will minimize its cost? The other side is a river. So the remaining 2 sides is $10 per foot. And they gave us the measurements. And they are running parallel, so it will be the same. So here the cost for the fence use will be, let's go back 1 second. First, I want us to see that the cost for the fence is 15, and the other 2 sides is 10 and 10. So we have That's why we have 15x. S is the measurement in foot, but 15 is per foot, so it's 15s. If the measurement is only 2 feet, then it will be 15 times 2. The same thing applies to the y. Y again is the number of feet, and here also s is the number of feet. They are perpendicular, para here. The x and x are para, y is perpendicular to them. So here we said, okay, if that's the case, the cost function for the fence use will be 15x this side plus 10y plus 10x. This is like finding the parameter of the three. The last is the river, so we don't need this part. So 15s plus 10y plus 10s. And we combine the like terms, so we get 25s plus 10y. Now we say we cannot use derivative to find where c is minimized unless we write c as a function of x or y only. Remember here we have two variables now, so we can find derivative of it, x and y. Remember all the time derivative have only one unit input. So we cannot use the derivative to find where c is minimized unless we write c as a function of x or as a function of y. Because the area of a rectangular field must be 1.6 million square feet, we have, or the area will be x times y, which will be 1.6 million. So here we can solve for y in terms of x and substitute, give c as a function of x. So what we're saying here is that a equal to xy, which is 1,600, 1.6 million. To find y, it will be 1.6 million over x, and that's what we have here. Then we're going to substitute. The cost function was 25x plus 10. And remember here it's supposed to be 10y. So now y is what? 1.6 million over x. Now we can find the derivative of this function. Again, reading the question, we were able to come up with this cost function straightforward because $15 per foot plus the other part is $10 per foot, and the other side also $10 per foot. Now, the reason why we have y and x, because this is a rectangle. The para side are the same, and also the widths are the same. So the width will represent it with y. But we have only one width because the other part is river. So that's why we have x and y here. Now, from the question, we say the whole area, we say a farmer needs to enclose a rectangle pasture containing 1.6 million square feet. So that's the area of the whole, the area of everything. So I can say area equal to the s times y. And I know area is 1.6 million equal to sy. So I find y, or you can also find x and substitute with y or y's. But here we decided to find y. And when we get y, we substitute and we get the x. Now with this function, we find the first derivative of the function. And this will give us our solution. Then after that, we equate the, again, I won't go through this step because the original function is here. We can bring the x to the power -1. That's what we have here. And here we are using the addition. So the derivative of 25x will be 25 plus. The derivative of this will be -2. -2 times, so that will double this to -32. So we have x -1 to, s -1 to -1. So s will raise to the power -2. And the front we have -1. We know the exponent power Sn is n times s to the power n minus 1. So we get 25 minus 16 million, s to the power negative 2. And we have this. Now we are going to equate our first derivative. If we like, we equate the first derivative to 0 so that we find the relative maximum or minimum, just to make sure if our solution we are going to get will be relative maximum or minimum. Other than that, we can plug the original graph, maybe using a calculator. Then from here, we equate the S value that we get, which will be the critical value. We get plus or minus 800. Here we are going to use only plus 800 because this is a measurement of space area. So in this case, rectangle. So a measurement of a space cannot be a negative value. So we use plus 100. So here we are going to, plus 800. So here we are going to equate this plus 800 into original function to find the absolute, if we know if it's absolute minimum or maximum. But first we need to plug the original function in using calculator. Or we can do the steps we did previously. We are going to find the relative minimum and maximum. Or here we decided again, S is 800. Negative 800 is meaningless because again, this is measuring space. We can have a negative value. So now we want to test to see whether S equal to 800 gives the minimal cost. So we find the second derivative of the function. And we see if the second derivative of the function, we use the S value of 800, the value will be greater than 0 or not. So here we say greater than 0 for every S, just by looking here, every S that is greater than 0 is greater than 0. So which means C at S is concave up for all positive S value. Again, we talk about concave up and down when we want to find a point of inflection or concave up and down, we use second derivative. When we're looking for relative minimum and maximum, we use the first derivative. So here we saw that we are concave up for all positive S value, got greater than 0. So S equal to 800 gives the absolute minimum. So C 800 will give me, so I will plug the 800 into my original function and I will get 4. Anytime we're looking for the absolute value, we plug the critical value into the original function. Now, if I'm looking for whether it's relative minimum or maximum, then I can plug the critical value inside the first derivative function. Or in this case, if I want to check if the function is concave up or down, then I will find the second derivative and I'll plug the critical value into the second derivative. And now if the answer is greater than 0, as we see here, then we say it's concave up, which means we have absolute minimum value. If it's concave down, we have absolute maximum. Concave down means the second derivative at x, whatever the s value is, in this case 800, our answer should be negative answer. Then we are concave down and we have absolute maximum. So here, the other dimension, so from here we're able to find the cost. So we know the dimension now. The area is 1,600,000. So we divide by 800, that will give us 2,000 feet. And if we can see from here, again, the graph, you can see it's again, minimum. So again, S at 800. Y is 40,000. That will give us the minimum. So let's try another example here. They say next example is inventory cost model, in which S items are produced in each production run, and items are removed from inventory at a fixed cost constant rate. Here we say because items are removed at a constant rate, the average normal store at any time is S by 2. Also, when S equal to 0, new items must be added to inventory from production run. So the number of units in storage changes with time, as we can see. So in this model, there are costs associated with both production and storage. But lowering one of these costs means increasing the other. To see how inventory cost models work, we should consider the next example. So here they say, suppose that a company needs 1 million items during a year, and that preparation costs are $800 for each production run. Suppose further that it costs the company $6 to produce each item and also $1 to store an item for up to a year. If each production run consists of S items, we should find X so that the total cost of production and storage are minimized. So a company needs at least 1 million items during the year, and that preparation costs around $800 for each production run. Now, suppose further that it costs the company $6 to produce each item and also $1 to store an item for up to a year. If each product run consists of S item, find X so that the total cost of production and storage are minimized. So first we need to come up with our function. What is the total production cost? Based on our question, we have the number of runs, then we have the cost per run, plus the number of items, then cost per items. This is equal to the 1 million during the year. And here we represent X. Then times 800, because 800 is the preparation cost. And the preparation are 800 for each production run. So 800 for each production run. Plus, again, 1 million times 6, because the company, again, it costs the company $6 to produce each item. And also $1 to store an item for a year. So plus 1 million times 6. The company needs 1 million items. So $6 per production cost. So we're going to have the total storage cost as average normal stored storage per item, which equal to, remember, it's $1. So average will be X over 2 times each cost, $1. That's the storage cost for each item. So now the total cost for the production and storage will be our first equation with the production cost plus the storage cost also. So this will be our total cost for both production and storage. So from here now we can again try to combine the like terms, open the parentheses, and we combine. This is what we finally get. Then we find the first derivative of the. So from here is the same step again. Find the first derivative of the function. Then we find the critical value. Equate the first derivative of the function to 0. That's what we have here. Then we find the critical value, and that gave us plus or minus 40,000. Again, we don't need the minus, we need only the plus. Because S must be positive, we test S to be 40,000 because S is number of units. It cannot be a negative value. So we test with the second derivative to see if it's concave up or down. So we say it's greater than 0, then we are going to find the absolute minimum again. Same as the previous example. And the second derivative with the critical value is positive answer. So that means we have absolute minimum, which means concave. Then if that is the case, we are going to, we have X 40,000 and we are going to store it in in our main function, and that will give us the absolute minimum. So here we are looking for the production of 40,000 items will yield the minimum total cost for production and storage. So we are going to end here with these lectures. And again, wish everybody the best. If you have any question, send an email. Thank you for your time.